This information is brought to you by Charles Sturt University.
So, welcome back to the class. So, just recapping what we were doing last lecture. So, last lecture I was introducing the concept of algorithms. So, what's an algorithm again? Yep, it's a recipe or a bunch of steps. From your point of view, most likely it's just going to be a computer program for intents purposes. So Turing's definition of an algorithm is anything a computer can do. Actually, if you can't ask a computer to do it, it's not an algorithm. Which is a bit circular perhaps, but that's it. So we want to look at, well, what sort of things do you want to consider when you do algorithms? And it's a bunch of steps. It's got to be done in a finite amount of time using a finite amount of space / memory. And so trying to check if algorithms or data structures, which one's better or worse or one another, is to understand how much time and much memory it takes to do various stuff. So what I looked at an example of two different data structures for storing data. It's two different ways of doing lists. One was a singly linked list, and the other was an array. And they just have pros and cons, effectively, at the end of the day. Like, it's not as one's universally better than the other. They've got weaknesses and strengths. And understanding those is good, and looking at how quickly or slow various operations we're doing was useful. And it's called time complexity. And often looking at the worst case is a key scenario. And the next thing I did, which is just the end of the example here, is looking at comparing different ways of sorting data. So if you had a bunch of data already in existence, how can you sort it? So one way is to do what's called a selection sort, which pretty much means find the maximum, pull it out, you just will list, find the maximum again, pull it out. So just keep pulling the maximum every single point in time. That normally means do lots of comparison and just put the maximum in the list fully, just do a swap. That's how you do it in place. And so we found that the number of steps required or number of comparisons required for a selection sort is less than n squared, where n is the size of the list. And then n squared was found really roughly, it's a tighter limit than that. But we did that way just to do a rough check. And then the other way of doing it is called a divide and conquer sort, where you pull out an element at a time. So you've got your pre-sorted list out, and you just keep adding one element at a time to put in order. And how you add an element in an already sorted list, you just go to the middle and you check how it compares to the lower element. If it's smaller, it's in the bottom half. Bigger, it's in the top half of the list. And so every step you're dividing the list in half. And so the number of steps required then to insert it is no longer the length of the list, but it's log base 2 of the elements in that list. And so we did some work last week. That's the calculations we did. Show that therefore an upper bound for the total number of steps to sort of the whole list using that sort of idea is n log base 2 of n. And log base 2 is a button you calculate it in some regard. It's basically, if n was 2 to the power of 10, log base 2 just tells you the power. So log base 2 is just a way of telling power. That's essentially what it does. So now we've got some ways of counting what the time complexity is, just how long it takes to do these algorithms, which one's better. And so it's good just to give a sense for how different they are by looking at some numbers. So I've just got different values for n, so how long the list is, values for n squared and values for n log n, essentially. Just plug it in. So the list is pretty short. It's pretty quick, no matter what. But as you can see, as you go up, as the list goes longer and longer, n squared does get quite big, much bigger. But the n log n doesn't increase nearly the same sort of level. So if you've got small lists, it doesn't really matter what you pick. They're all going to be done in so quickly you never notice how long they take. But when the lists get really, really big, you can see that the n log n scales better. And so what matters here is the fact that it's only 10,000 or less than 10,000 comparisons rather than over 1 million comparisons. The n squared operation. So which if you had a really large data set, which sorting technique would you use? Yeah, the divide and conquer one, or things based on that. So, I mean, the divide and conquer is a bit theoretical, I want to mention. So a more one that based on that's more of a heap sort is how you actually can implement it. But there's other ones similar to that. So anything that sort of divides them in half somehow or other, which is what a merge sort does, which is in your assignment task, really is going to get some more efficiency. So you can see that n log n is, so it's closer, if you compare the numbers, that the n log n is closer to n than it is to n squared. That's the other thing to notice. So what's going to be, therefore, this is just an illustration, but the bigger picture is we ultimately will like to compare functions and see how they grow. If you've got small stuff, it doesn't really matter. You can just do a really bad job of coding it up. You still will get your computer's quick enough not to get bothered by it. But if things grow really quickly based on the data set, that can really stuff you up. And so understanding how the time complexity grows is a really useful idea. And in the end, we don't really need to care about the precise details of what the actual number is of how many seconds it will take to be, because you just always get a faster machine that's a little quicker. Right? So what we want to know is that growth factor, or the growth class it's in, is more important. And so the way of trying to capture that, a common way of talking that is called big O notation. Why is that funny?
There's something C in maths.
Okay.
Big O.
It's the answer big Omicron, even if you want to go nerdy, but it doesn't have such the same ring to it, I guess. So it's a common way of representing it. The better way of doing it is probably using big thetas, but for some reason that's not so popular, so we'll big O's. I'll mention thetas in a little bit. There is slightly better ways of talking about it, but this is the one that's commonly used. It's more like basically it's just trying to describe how things grow is really what it comes down to. And it's used for both talking about time complexity, and it's like an upper bound, so it's really like a greater or equal to, or less than or equal to idea. It's talking about upper bounds for how things grow, essentially the idea. You could use it for how much memory gets used, or time, both, but we'll look at just time primarily in this at the moment. Okay, so this is the precise definition. So you got a function, so a function that's sort of fn, non-negative function. It's in this growth class big O of g of n, so I read it out, big O of g of n, if fn is bounded above by some constant t times by the function for big enough numbers. This is what it says. So, what does that mean? That if you make things big enough, f of n is or grows slower, or maybe the same speed as g of n. So g of n always growing faster than f of n, putting it the other way, or at the same speed of. Could be similar. So in some sense, in terms of growth, f of n is less than or equal to the growth of g of n. Is another way of putting it. So it's all about comparing how things grow. So that definition there, which is so the f of n is less than or equal to t g of n, is the formal definition. I'll use it briefly, just so you understand what it's on about. In practice, though, we will normally use rules of thumb to work out, to compare big O notations. So to compare the growth of different sorts of functions. So we won't use that definition very long, but that's the formal math definition for it. So in calculus, you do limits, that sort of stuff. Has anyone done limits?
Yeah.
So you can define this in terms of limits. If you don't know what it is, you can ignore the whole slide. But essentially, if you take the ratio of those two, so the ratio of Fn and G of n, if that limit's infinite, so not infinity, that implies that f of n is in the big O of G of n. If it's so much that it's equal to 0, that suggests that Fn is even strictly smaller in terms of growth in G of n. Which says a lot, actually says a lot. So you can do all this in terms of limits if you wanted to, but since many of you may not have done much of that at university level yet, I'll skip it. But it corresponds to the idea of dominance that I would say talk of Maths 101, which some of you might do next year rather than today. So let's just use that formal definition to get a sense of something that's bigger, and then we'll look at the more bigger rules. So I want to show that this particular function here, so that could be, how many operations are required by a function, show that's in the growth class of big O n cubed, essentially. What you're trying to say is when n gets really big, when n's big enough, essentially this function grows like n cubed or something slower than that. That's sort of what the idea is. So it certainly doesn't grow any worse than n cubed. So, how to prove these things formally, which is what I'm going to try for the moment. I've got a function f of n, and then I'm trying to prove it's in this big O of G of n class. Let's be short. For really short, let's call it f and g. I pretty much need to say that f here is less than or equal to t, some constant t, times by g, for when n gets big enough. For n greater than some number. So the t here and the m here are mysteries. We don't know what they are. You can pick m can you pick lots of things for, but we have to work out what the t and the m are to make it actually concrete. So that's what we need to do. So this is that's the strategy. So the strategy is to find an m and a t to satisfy that sort of constraint. So pretty much as make n big, this is what this one says, so as n gets really big enough, then f is bounded above by some constant multiple of g. So g is always, by a constant multiple bigger than it, essentially. So let's just have a look. So let's write an f. So pretty much what I want to do is I want to say that's less than or equal to something times by n cubed. That's the goal. So let's look at the first one. Well, let's do term by term. So it's certainly believable that 4n cubed, well, that's already a constant times by n cubed already. So I can sort of just leave it as it is. That 4 is going to be part of my constant in a second, so that's all okay. This next term here, I would like to say that one is less than or equal to something times by n cubed, just to get this sort of pattern going. So what would I pick? Well, n cubed is always a positive number, minus 5 something or other, minus 5 minus n squared is always going to be negative. So I could just be really lazy and say that minus something or other is going to be less than or equal to 0.
Is n cubed always going to be positive?
I can just make sure that I just pick positive ones. So so as long, we're only concerned about when n gets big, so we can ignore all the negative cases.
Right.
So in practice, n's often going to be the length of the input. So in negative inputs are just irrelevant. Sorry, the last one was 6n. So I want to say that's smaller than something times by n cubed after a while. So here's a little trick. So if you say if n is greater or equal to 1, which is pretty much a pretty easy thing to say, then we can say that n would be less than or equal to, therefore that's the same as saying 1 is less than or equal to n. It doesn't really say much different. It's just flipping it around really. So you've got n's greater than 1, 1 is less than n. And so you can multiply both sides of that last equation by n as many times as you want to. So I could say n is less than n squared, for example, and etc. And what I could do is I can multiply, and therefore 1 would be less than n would be less than n squared. And I can multiply everything by n again, so I can see that n is less than or equal to n squared, less than or equal to n cubed. All of them will work out. So what we see is once you get n bigger than 1, I can say that n or n squared is always as you get bigger powers, they just get bigger and bigger. And so what I can say over here then, in particular, is that 6n would be plus 6 times less than n cubed. So n would be 10. If you plug in 10, for example, if you cube that, you get 1,000, much bigger. So cubing a number is always bigger than the number itself, so long as you're bigger than 1, essentially. So once n gets big enough, not very big at all really, the cubing is always bigger than just leaving the number by itself, essentially. So what I've got here is a bunch of terms. I can put all the constants together. So this is equal to something times by n cubed.
10.
So it's 10, yep. And I did that once n was bigger or equal to 1. So I had to use that condition there to put it together. But once n is bigger than or equal to 1, that's only true. This whole expression of f is less or equal to some constant times by n cubed. Yep.
What have you got written above n is greater than or equal to 1?
Once.
That's once.
Yes.
I can't read that.
I'll not use running writing. That's the word for it.
I think that it doesn't really work very well with the smart pen.
It blurs it even more than my normal writing is, yes.
More like a dumb pen.
It is a smart pen because it actually says the word smart on it.
That's the brand name.
It's the brand name,
Not
yes. Rather than necessarily the intelligence of it. So what have we done? So that basically says we've got f is less than or equal to some constant, 10, times by g of n, for n greater or equal to some number, n. So that's what we've done. So essentially we've gone f of n is bounded above by a constant multiple of g of n. That's precisely the definition of f of n being in the big O class of g of n. That's a very formal way of proving it. And given your faces, I would suggest that's probably not the way you would like to do it most of the time.
How did you get the n was greater than or equal to 1?
Oh, I needed that, so...
Yeah, but like, how did you... Yeah, I know, but like, how did you just get it? Like, where did it come from?
It just is, David.
It just always is, is it?
Oh, no.
Greater than or equal to 1?
So, it was that going from the two thick and red circles there. I wanted to say 6n was less or equal to something or other times by n cubed. That's what I wanted to say.
Yeah.
If you picked 0, if you picked a half, for example, n is actually bigger than n cubed for n equals a half. So to get that less than or equal to work there, I need to have big enough n. Big enough happens to be 1.
Oh, okay.
So I needed to push it that little bit bigger just to guarantee that less than or equal to for that part of the expression.
Thank you, Becky.
That's all I did it for.
Makes sense.
So that's a very formal way of doing it, exceptionally formal, as you'd imagine. And since I'm not sure how good your algebra skills are, this is algebra with inequalities, which is a whole more greater difficulty again. And so let's try to avoid that where we can. So what you need to understand to actually use this stuff is to understand how they compare with each other, to realise which things are different. So something to learn from this, a few things, is more what we've concluded at the top. So let's just copy that again. So we've pretty much we've got a polynomial, and so with big O notation, it doesn't really care about constant multiples. It really just ignores them. So the fact there was a 4 at the front of it didn't matter. It really doesn't matter, because all that affects is it just affected this constant here, which sort of just disappears in the long run. So we don't actually care about multiple on my constant multiples. You're thinking, why? That doesn't make a big difference. If I can reduce the amount of time an algorithm takes by a factor of half, like you multiply by half there, wouldn't that be better? And the answer is, of course it is. But often that would be information dependent. So if you get a better machine, of course it's going to be done in half the time, whatever it might be, if you measure the time correctly. So that's, and it can be how you might implement the underlying machine, which you may not control. You can control your code, which is high level, but not the hardware, etc. And so changing the algorithm to a different machine will quite change this time complexity, but we will still just care about the growth, how it grows. So that's one of the simplifications that Big O has, which is sometimes good. It isn't always helpful. That is a weakness of it, which I'll talk about more later. So we don't care about constant multiples. That's the first thing. Second thing, when you have a polynomial like that, all that really matters in the long run is the highest power. So the fact so n cube's the highest power here. So I had to have an n squared and an n. Don't really make much difference when it comes to how it grows. It's just the largest power which really dictates the long-term growth. So when you've got any polynomial, just look for the highest power. That's going to be that will tell you the most information, and then ignore any constant at the front. So, for example, give you some random numbers here.
17.
17 and
264,321.
Well, I won't do that big.
Let's just go with 4.
264 plus another number.
That's pretty big.
9.
6.
6 end of the 9.
Oh, damn it, David.
Plus 12. Plus 12. Okay. What is the Big O class for that? Well, this would be in Big O. Well, effectively, the easiest class we're going to deal with is essentially we look at all the terms. We look for the highest, the term with the highest power, which is that first one there, 264. Much bigger than everything else. The other terms really, as n gets bigger, these terms here grow much slower than the other one. So if you sub in n equals 2, for example, 2 to the power of 264 is much bigger than 12. And so already by n equals 2, that last term sort of has disappeared into nothingness almost in comparison. So these terms don't really impact how it grows. It's really just the highest term. That's the only thing that's going to matter.
And in this case, it's very big.
Yeah, much, much bigger. That's right. And the constant at the front doesn't affect Big O, so we can just sort of drop it as well. So the Big O for this, the more simple way of writing it down would be just the biggest, highest power will drop the constant. So n power of 264. And if you had an algorithm with that sort of complexity, I wouldn't do it, essentially. It's not a very efficient algorithm. If you get like n squared variable, that's not very good, essentially. That's right, which is the matter.
I disagree.
So n equals 2 and you realise just how slow the algorithm would go, essentially, if you input of size 2. So that's the Big O notation. Again, it's just measuring how it grows. And so if you've got large inputs, that number gets really big way too quickly to make it useful in any real algorithm, essentially. So there are some tricks for proving them the formal way, so I'll avoid those where I can. Let's just do one more of these formal proofs just to get some other sort of concepts going. And then I'll start talking more about the rules.
Oh, there it is.
Okay. So let's try to prove formally that n squared is in Big O of n cubed, which is effectively a way of saying that n squared grows slower or at the same speed as n cubed. That's the first one I was trying to say. And secondly, that n cubed is not in big O of n squared. So n cubed doesn't grow slower than n squared. So effectively what that really means is saying that n squared grows strictly slower than n cubed. That's what effectively those two mean. So, how do we prove this? Well, I need to prove that n squared is less than or equal to some constant multiple times by n cubed. So, the way to do that is to write this down as 1 times by n squared. That's the first trick. And then so if I insist that n is greater or equal to 1, which is a pretty easy statement to make, so as long as n is big enough, then the 1 there, this one here, must be less than or equal to n. So all of these are just, I got that inequality, just swapped it around, put it the other way around, that's all I'm really doing here, times by n squared. So those two bits really just match up to that statement precisely. So it's that little same trick I did before, really. So if you make n greater than or equal to 1, you can say any power is less than or equal to some higher power. So I've got n squared is less than or equal to n cubed then. And that's the precise, and so for n less than or equal to 1, and again let's make it really clear, let's put number 1 there. So I've shown that n squared is less than or equal to some constant, that's a constant there, 1, times by n cubed once n is big enough, once n is bigger than 1 in this case. And that's the precise definition for saying that n squared is in the big O class of n cubed. Which is a super fancy way of saying that n squared is growing slower or maybe at the same speed as n cubed, essentially. Yep.
What's that pointing to the 1?
T.
That's T? Okay. Sorry, before handwriting
No.
down
Cross Jesus was crucified on. It's really hard to see.
It looked a bit
And
funny.
why I used T was to match up this notation, which is not your question, I know. It's much more lexicographic than that. Anyway, so that's just that, looking at T there.
See, now, oh, there we go.
Yeah, so that's the first bit. And let's do this last one. How do we show that something's not in a big O class? So, it's a negative thing. So let's try to think back to proofs. If you're trying to prove something negative, it's often easy to do the opposite. So let's do a proof by contradiction. Let's assume that n cubed is in the big O of n squared, aiming for contradiction. So if n cubed is in that big O class, that would imply there is a m and a t such that n cubed is less than or equal to t times by n squared for n greater or equal to m.
Triangle.
Is it actually a triangle? Or should it be something else?
This thing here, ampersand.
Okay, right. Yeah, I know that, but I asked Corey, and Corey said, that's a triangle.
Okay. So I was just going, well, it's a negative statement, let's just do, let's try proof by contradiction. First step proof by contradiction is just say, well, I made an assumption, translate what that means, and see if we can muck around. So what I'm aiming for is hopefully that's false, essentially. That's what I'm hoping for.
And therefore it must be true.
So, yes, it's proof by contradiction. That's the whole idea. So once n's greater than or equal to n, so in particular, what I can just insist that m here is positive. That's not a big result. So if n was negative, for some reason I can just make it bigger. It's not easy to just make n bigger if I wanted to. So I can divide both sides there by n squared. So I just divide both sides by n squared. And so I get that, just divide by n squared. And see n cubed divided by n squared is equal to what? N. N squared on n squared is equal to
1.
1. So it's not even bother writing it down even. And so what I've shown is that if n cubed was in this big O class of n squared, then what I would have to conclude is that once n is bigger than a sufficiently large number, it ends up being less than t. And that doesn't work. If you're allowing n to be as big as you want, you can't then conclude that it's bounded. It just they don't work. They don't match up. So that's a contradiction. Since n can't be as big as you want, and n less than or equal to t. So you can't say, oh, I want n to be anything I want to at all, and then start restricting it to be less than or equal to some other number. They just they contradict each other. And as soon as you got the contradiction done, essentially, let's put something fancy. Say QED. I've explained that one before. So QED is one way of just finishing off a proof. It's from Latin, so quod erat demonstratum, which is a very fancy way of saying that's what I told you I was going to do, essentially.
So basically math.
I always like to be more precise than doing maths.
It's like damage control. It's like I meant what the answer. I mean, that's what I meant to do the whole time.
Oh no! It's instead of writing another sentence saying therefore the result's true. That's what you normally do. You just say, oh yeah.
It's like I meant to do that. I'm gonna run it all my stuff. It's like, oh, the answer.
Okay, so that's the last of the formal ones we'll do, which I'm sure you're glad of.
Image optimization. That's good maths right there.
So what's the conclusions can we draw from this? Is that you can see that it's not an equal. So it's sort of how it works. It really is something like a less than or equal to. So what we really should have shown is that n squared is less than n cubed in some sense, in terms of how it grows, but not the other way around. So there are fancy ways of sort of trying to show this. So I'll mention just on this slide only. They use little o to indicate the less than idea. This is little o. It doesn't get used very often, but the n squared grows strictly less than n cubed, sort of what we've concluded here. So the n squared saying it's sort of like less than or equal to. This one's saying it's not. So this one's trying to sort of translates to saying that n cubed is not less than or equal to n squared. That's sort of what it translates to being effectively in terms of growth. And so putting those together, that really strictly says that n squared is less than n cubed. That's sort of the only way of concluding it. So the way to write that down is using what's called little omicron or little o. Now, most of the time, people don't bother writing down little o's. They just like writing big O's for some reason. So that's just fine. There's nothing wrong with that. But so what we want to do is, you can see that as you get higher powers, basically they really become separate classes. So there really is an order to these big O classes. And so what I want to say then is big O of n squared is a strict subset of big O n cubed. So all functions which have big O n squared are strictly quicker, effectively, or don't grow slower than anything in n cubed. That's more the conclusion I want to draw. So if you've got an algorithm of n squared, that's better than n cubed. At least when you've got bigger inputs. For small ones, it can actually go the other way around. But when your things get bigger, n cubed is better than n cubed. N squared is better than n cubed. Or a quadratic function is better than a cubic function. Or a quadratic algorithm, etc. So some other things, just the amount of fancy notation. If you want to say the sense of what equals might be, it's sort of theta. So we had before, so 4n cubed minus 5n squared plus 6n. We said this was in big O of n cubed before. That's still true. But sometimes you want to say it's equivalent. So actually, they actually grow the same way. So what I could do is I could show that's in big O of n cubed and the other way around. I could show that n cubed is in big O of the n cubed minus 5n squared plus 6n. So they're sort of equivalent to each other. So in terms of how they grow, they're equivalent. So they use big theta. Which sort of means grows the same. So they have the same level of growth. They're equivalent. It's really just the same equivalent to each other. And so the better notation for this is probably big theta. It just doesn't get used very much for some reason. So whenever you use theta, big theta, you can always replace it by big O. It's still valid. So big O is just trying to say, big theta is just trying to say equals. That's what it really corresponds to. And so you can always replace equals by less than or equal to. It's always valid. And so it's sometimes easier to say big O, where theta requires a bit more proof if you're going to do it formally, which is why I thought maybe I'd do it. So that's just some things. So let's go back. Let's look at the rule. Look at some the rules on this. Okay. Yeah. So here's basically what this all suggests. There's a bunch of separate classes for how things grow, and they all have different big O classes. So if you've got integers, O to some power is strictly contained in O in another power, so long as you've got different. So for example, like I said there, big O of n squared would grow slower than big O of n cubed. And if you pick any numbers, like big O of n to the power of 32 would be strictly contained in big O of n to the power of 64, because it's strictly smaller. So higher powers just grow quicker, as I sort of said before. There are some other ones worth noting. So big O of 1, that means that's a function that just does a finite number of things. It does the same things regardless of the size of the input. Might be 50 or 100, but if you have a really big input or a really small input, it always does the same thing. That's what big O of 1 would be.
So we need to remember that entire thing right there.
Yep. So remember it. It's probably worthwhile. It's good to internalise it. You've got a formula sheet for your exam, if you recall.
It's pretty easy to remember anyway.
So the tricky one is that one at the top is straightforward, and that's sort of what you expect it to be. So give some names for it. Big O of 1's called constant time. So they're functions that are done in constant time. It really doesn't care. It just ignores the input. That's the idea of constant. Big O of n, they're negative powers. You don't see those very often. I mean, that's not a very realistic algorithm. This one is big O of log of n. Now, most of the time in practice it's probably log base 2. Because big O doesn't really care about constants, you can drop it out of the notation, like I've got there. That's why it doesn't get written down. So log of n is called logarithmic time. That's the name for it. And they're much closer to this sort of thing. So after logarithmic time, you've got all the different. This O to the NA is polynomial time. Then the next one it goes up is called exponential time. So anything that's exponential grows much faster than polynomials. This one here would be factorial time, which is pretty bad, essentially. And the last one, if you ever get to that stage, then forget it. Essentially, I mean, you would forget it earlier than
It's
easily.
just too big.
I can't think of any. I can't think of any off the top of the head which actually have big of that last case. I've got some examples next slide. So breaking it down, this first bit, just seeing where the logs ones fit in. So ON is linear time. So n log n is between linear and quadratic. And so the ones down the bottom here are the ones you'd see in algorithms actually run quickly, essentially. So you're going to remember that all. We'll sort them in a second. So just to give you some ideas of these are some different functions, just to show you how bad some of these latter ones are. These are some of the different functions. I've got actual functions here, but the big O would suggest the same sort of class as these. So big O of 1 would be something like constant time, like adding to the front of a stack. So just putting one entry into the front of a stack. Or adding something to the end of an array. It's just one thing it does. Who cares how big it is already? If you could do, say, 1,000 operations in a second, which would be a pretty slow computer, then this is how many seconds it would require to do it. It's constant time. It's the same regardless of the input. It's always really quick. Adding to a binary tree. So if you've got a balanced binary tree, then adding to the binary tree would take log base 2 of the size of the tree, the number of operations. And so this is the time it would take to if the tree was size 10, 100 or 1,000. So you can see it's still pretty quick. You wouldn't even notice it. For a tree of size 1,000, adding one more element is going to take 0.01 seconds on this very slow computer. If you've got a function which is linear time, for example, you have to find them. If you have to sort, that's just basically a single loop, just looping over a list sort of thing. That would be done in linear time. So lots of those things, like finding the maximum array or minimum. That's the time. You can see it's starting to get a bit slower, but still often done in 1 second. N log n is commonly seen for sorting stuff, like sorting arrays. And you can see that's a little bit slower than linear. So that's called quasi-linear is one of the names. There's lots of different names for that one because people can't agree to it, essentially. But that one's close. So n log n is just a little bit worse than linear time. That's one good to think about. The next one will be n squared. They're called quadratic time, like a bubble sort. And it's just interesting to compare these 3 rows here. So if you've got a set of size 1,000, it took 1 second for just a single loop. N log n took 10 seconds, so 10 times longer. It certainly takes a bit longer, but then n squared is 100 times more longer. So n squared takes a lot more time than n log n if the constants were matching up. So therefore, n squared is anything like a nested loop, so you've got 2 loops nested. That's an n squared algorithm effectively. So you can see if you can ever try to redesign them to make an n log n, you're normally going to get much better time, much better scalability. And so the easiest ones to talk about are the sorting algorithms, so they're quite well known. And so people, 50 years ago, thought really hard out how to sort data and come with some rather efficient algorithms, which people tweak every so often. So the ones that would be in the languages you've used, like Python and Java, for example, are tweaked versions of ones which people developed about 50 years ago, but just tweaked to the system. So anything up to n squared, that looks bad, but still, that's just a nested loop. That's doable. You can live with it. And like I said, this was a slow computer anyhow.
A very slow computer.
Yes. Very slow computer.
Jono.
Oh my god.
So it's interesting to see how it compares to the next. So the next sort of class is exponential. So this is 2 to the power of n is an exponential, and that would be if you had to consider all different possible subsets of something, that would be a size 2 to the n. It would be some sort of unusual looping. In order to if the set was size 10, It might take you about 1 second to do that. If the set was size 100, and you want to consider all subsets, it'll take you a long time on this. Now, this is a slow computer, but even if the computer was, a million times quicker, which is not unrealistic, that's still a long time. So exponential time really is bad. You don't really want to do it. The worst one still is called n factorial. So doing the travelling salesman problem by brute force without any trickery whatsoever. Try directly by brute force. Doing on a size of on a set of size 10, it would still take you 3, whatever that is. So that's an hour, isn't it? So it takes about an hour of computer time. That's pretty bad already.
That's a slow computer.
And it's a slow computer. But it's interesting to see how it scales. That's what all the thing is. You can see when you get to 100, it's growing pretty badly.
I wonder what 1,000 is.
I
wonder what 1,000 is.
It doesn't really matter by that stage, isn't it? So the travelling salesman problem, you can use a bit of trickery to prove it by brute force by bringing it down to exponential. So you can actually reduce travelling salesman from this sort of class to the one below it by using some trickery and still get an exact solutions. But still, you can see it's normally not very good. And so, unless you happen to have lots of computers in parallel trying to solve it, which is people have done that, the other way is just to say, I'm not going to try to solve it exactly, I'll try to get a close answer instead. And so it's good to understand your algorithm. You go, look, I'm starting to get these bottom few classes here. It just isn't going to be worthwhile trying to get the computer to do it properly. It just will slide away. It will just never get there collectively. And so you have to think, I have to do something different. Maybe I have to do it approximately rather than exactly at that point in time. So understanding the order is useful when you look at your algorithm and you go, I can affect it. So the number of nested loops would give you big O n to that power. So if you had 4 nested loops, that'd be n to the power of 4, for example. Which I haven't written down, but it'll be somewhere between these two rows here. So somewhere between OK and forget it, essentially. But no, n of 4 is 4 nested loops would take a lot longer than just 2 nested loops, as you can imagine. So understanding how things grow is important. So let's just have a go at marking this around to some. One. It isn't that bad.
It's not pleasant by any means, though.
It was quiet for the first chunk of the lesson too, which was weird.
I don't know what James is. So I've got 3 functions here. So what I want to do is I want to find some big O class that all will fit into. Just to make it simple, I want them to make them look into big O of n to some power. And I'll make them integers. I'll only say that integer. So ON or ON squared or ON cubed, whatever it might be. So given various functions, I want to just get a simple big O class for it, and I'll make them integers, etc. So here's some tricks to how to do that. So with this first one here, if you've got a polynomial, really it's the largest power which is really going to dictate how it grows. And so I can ignore the 3n. Because I'm just looking how it grows, the n squared will really dictate how it's going to grow more than anything else. So I can sort of omit that. And then what else can I do? Well, any constants don't really make any difference for big O. So I can forget the 5 too. And therefore this is going to be in big O of n squared. So therefore this original function here, so if you had an algorithm that's on number of steps, I just call it a quadratic. It grows in the same sort of way as any other quadratic function, up to a constant. That's sort of the trick there. So just pick the highest power, trim all the other ones down, and ignore constants. What about this one here? Well, this one's not a polynomial anymore. It's n log n times y log n. And so if you've got a product, you can sort of do them separately. So log of n is somewhere between constant time and linear time, essentially. And so big O of n log of n squared. So especially, inverse multiplying of n is just a little bit more than constant. So effectively, look at the wrong stuff. So n log n. So n log n is a subset of n cubed, and we can do the same sort of thing again. So it's effectively really close to constant time. So each of those n log n's give a little bit more, take a bit more time to do, but not much more time. And so we have to jump up to the next power. So what's the next highest power after n to the power of 1? N to the power of 2. So this n square, the log n bit means it's going to take, it grows quicker than just if it was just linear, just n by itself, but not much more so. So it only ever goes just up to the next integer class. Okay. So that's sort of the smallest class we would do for integer 1. So for this bottom one here, we've got a division here. So the way to do that is I've got to consider how the top and bottom grows separately, effectively. And I want to consider, how it grows, I'm just worried about big N effectively. And so as N gets bigger, it's really just the highest powers which really dictate the growth of it. So for the top there, what term will dictate the growth for it? Yeah, yep. So the 4n cubed will really dictate growth. So when n gets really big, the 4n cubed will be so much bigger than the 2 to the n, you can almost forget it, which basically is what we're doing. I'm just not really writing it down. And so for the bottom there, what term would dominate the bottom?
5n squared.
5n squared. So if you sub in n equals 10, you're already up to 500 for the first term and only 3 for the second. You can already see that 3 is becoming insignificant. N equals 10. Let alone anything bigger. That's why I'm sort of not writing it down. So that sort of sense, just looking at the highest powers, top and bottom. I don't really have to worry about constants even, so they just disappear. And so this, so therefore, what big O do you reckon I'm going to be in?
N.
N. And how do you work that out?
Just get rid of the constants and then n cubed over n squared is just n.
That's right. Does that make sense to people? So strip the constants out so they never matter, for big O's at least, and then just go, it's n cubed on n squared, take the difference, you get just one n left on the top. So when you've got combinations of various terms, for polynomials just pick the highest power all the time. If you've got division like I've got here, again just strip each top and bottom back separately to the main class, and then just do the division directly. So we did a few of these a second ago. So I want you to we want to put these ones in order of their big O class. So the big O class would put the function which grows the slowest first. Which one would grow the slowest?
What?
0.1 and 4.
Now, if you sub in n equals 1 into all those expressions, that just shows you how it goes for really small data sets. We don't care. Some of them are quite maybe inefficient for small data sets.
But if you 50, 500,000?
I want to know how it grows. I want to know what it looks like when n is a million rather than n equals 1.
Yeah, 50, 500,000, that wouldn't grow at all.
And so the one that doesn't grow at all is this one here. So in terms of what I said before, this is a bit to remember, is that particular order, that's what you need to try to remember, right? That's what we're utilising. That negative powers, if they ever come up, would be the very bottom. They're not very realistic. Then you have constant time. I want to have no n's at all. Next would be log n. Next would be n. Then n log n, n squared, etc. So that's what we're sort of looking for. So we've got the constant time one. So that one is in big O of 1. So that's called constant time. So although that number is really big, it does the same. It does a lot of steps, but it does the same number of steps regardless of the input size. Now, does that make it a good algorithm because it's constant time?
No, not always.
Well, if it's going to take 500,000 steps, probably not a good algorithm still, is it? Maybe you could try to...
But what is that in reference to? Maybe something else will take a billion steps.
I say if you have a data set of like a million, 500,000 steps for a million objects can be pretty efficient compared to other algorithms.
That's right.
And then if you consider it with a data set of only like 100, that's 1,000 steps for every object. That's a bit intense.
So
I don't understand the overhead.
So when it comes, so Big O simplifies things down a little bit too much, perhaps. It talks about how it's good to compare growth, but it really does drop that constant, and those constants do make a difference. Like as you can hear, constants, 500,000. That could make a quite believable difference. And so that's a weakness of the system, and so it's good. And it's a good idea to at least appreciate that. But so you need to think of it more, compare things more broadly than just Big O, but you also need to compare it relatively, just like you talked about. So anyway, what's the next one in terms of growth? Which one would be next one in growth?
Would it be the 4n cubed plus 2n1? Because that's just n on its own.
Yep, so we did this one a second ago. So we said that one was linear time, in the last slide. And so what normally happens, you say constant, then linear, etc. So you just go from powers. What next?
Would it be 3n?
The one with the...
Okay, so what basically you do constant, polynomial, anything with polynomials in it. Then you do exponentials, and then factorials. And then n to the power of n if you put them around.
3n, 0, and 4n.
So we're basically, the ones we want to do next are all the different ones that are polynomial or equivalent to it. So what are the polynomial ones?
5n squared.
That's polynomial. That's...
Oh, the 5n squared is connected to the 3n. Oh,
Yeah.
okay.
Yeah.
I didn't see that.
So that's polynomial, and the rest of them are. So they're the two polynomials. They're the ones that are going to come next, those two. So just have to work out which one's which. So the first one here, we said before, that was in big O n squared, definitely. This one here, well, log of n is somewhere between constant and linear time. So the fact it's n times y log of n means it's going to be less, strictly less than n squared, really. So that one's going to come next. So in terms of how things grow, that will grow slower than 5n squared plus 3. So in terms of growth. So those ones are the polynomial time. So next thing we have to do, once you get all the different polys, next one is called exponential time. So any number, like 2 or 3 or e, as I've got here, to the various powers. So do you have any exponential ones here?
3 to the n.
Yep. Oh, I missed one, haven't I?
Yeah, the 0.1.
So that's also poly time. That's poly, and so the one after that would be exponential. It's exponential time. And the last things we would normally encounter would be factorial, which we have here. So in summary, you do constant. So in most more realistic examples, you have constant time first, then all your polynomial time ones, essentially, and the order is just in terms of the power. Logs fit it somewhere between. So if any logs, they sort of fit in between the various powers. Then you'd have exponential, then you have factorial, and even worse than that would be n to the power of n, which you're really hoping you're not having.
Would you ultimately try and, again, sort them biggest to smallest? Like, if you had a multiple constant time, would you then, like, order them so that the smaller ones come first?
Yeah, so let's do a more realistic example. So you wanted to sort some data.
Yeah.
There's lots of sorting algorithms. And so there are some algorithms like bubble sort, which are clearly inferior to merge sort, for example, or heap sort, because that's n. Bubble sort definitely n squared, where so there's lots of n log n's. And you go, well, okay, I can bubble sort. That's a slow one, so I just put that to one side. So I've got a bunch of n log n's. How do I compare those ones? And in that case, well, they're all the same big O class, but that's when you start knowing, well, they actually have different constants at the front. And you go, and then I need to start ordering them in terms of which one has the smallest constant, and that's the one I'm going to focus on. That would seem to be logical. There's some caveats there. Big O is only looking at how things grow. So it's really designed for looking at large data sets. So if you're trying to do something to something small, Big O really is not a good information for you. So if you want to if you wanted to sort a list which is pretty small, maybe bubble sort would be okay. By the way, it's pretty easy to cover up, for example. Much easier than some of the other ones. And so small data sets, you can actually get away with, you don't care at Big O for small stuff. That's all the weakness to it. Okay. Last one before I talk about the weaknesses. So this is a code fragment. And it would be better done using a for loop, I reckon, but I did it with whiles just to match up the assignment because some people don't know what a while loop is very well. I presume not you guys, but if you do programming...
If so, we've failed most of our assignments this session in Java.
I use a lot of while loops.
Not everyone does Java though, if you does this subject.
Well, look, while loops are pretty self-explanatory. Even like looking at it.
While that condition is true, it will do something.
Yes, that's it. Yeah, while's easier to understand than say for example.
For it's like basically the same thing. It's for while this thing does.
For what?
It's like the same thing.
Yeah, so if you know what each thing means, yes.
They're basically the same loop.
Do you want to explain it to the class?
Okay. So, can someone tell me what this is doing? I'm sorry, it should be typed slightly differently. It converts a tab, converts my space in the tab, and then doesn't explain properly. That's my excuse. But anyway, because I can see it, I can see things I don't like the look of in that spacing. But what's this doing?
It adds I times j to t for every I, while it's less than the number of items in the set. I think.
Okay, let me.
We'll take it and initialize, so it's not doing anything.
Well, tits.
I mean, what's the end? Who knows? It could be anything.
Oh my god.
David, get out. See you next year, Michael.
Okay. Let's suppose we have a grid. It's easier to understand it. So we've got I's and J's. It's I starts at 1. So I equals 1 to begin with. 1 here. At the bottom here, it's incrementing it. So it's going to do 1, then 2, then 3, etc. What's the largest I will ever get to? N. So here it is. It keeps going while I is less than n. So the last it ever does will be up to n. So this outside loop here this bit here is basically saying I'm starting at 1, so long as I is less than equal to n, I'm going to do something or other in the middle, and once I've done in the middle, I'm going to make I bigger, and just keep going over and over again. So, in case you don't know loops, which is not really people in the room, I gather, but people in the recording might be the case. So, you initialize it, you keep doing stuff, this is the stuff in the middle, and then once you've done your stuff, you've got to make I bigger, and once you get to the bottom of the loop, you just go up to the top again. And then you just check the condition. If the condition's true, you go into the loop, do it again. If it's false, you just go, oh, that's it, I've had enough, and go and leave it. So that's the outer loop in this case, just changing I from 1 up to n. There's an inner loop here, so there's another loop. There's this one here. And so it has an initializer, so it starts with j equals 1. And then there's an incrementing step, so at the end of the loop it just makes it bigger, one at a time. 1, 2, 3.
Until it reaches n.
Until it reaches n. So in terms of what it's looping over, effectively it's looping over this sort of rectangle here. So at each point in time, it's firstly working on I times by n. So it's working at different products. So I'll write a few down. So writing just my grid of products, that'd be 1, 2, 3, etc. 2, 4, 6, 3, 6, 9. So that would be all the different products it's going to do. So you can imagine there's a whole square full of numbers. What's it doing to those square of numbers there?
It's adding them to t, so it's creating an accumulator.
It's just adding them up. What you said is correct. So all it's doing is just getting at the whole square and adding up all those numbers. That's all it's really doing. And why would you want to know that? Good question.
It depends what n is.
Well, I'd say math is what it's doing, but for what cause?
Better functions ones, you'd have a few if statements in there to find a maximum, something like that.
If you want to try and you're just sampling nuclear codes here, and you kind of just like.
But I wanted to pick an example which, didn't have any break statements from the left.
I wonder how long this one will go on for.
Because then that would make it even harder for people to understand.
Yeah, correct, that's right. So what I want to do is, now I know what it's really doing, so t here is the value it's being adding to, and each part in the loop is just adding the next element you get from this square. So how it's running is that this first loop basically, so it's going to run the numbers that sort of way. So that's how it's going to go. So it's going to cross the first row, and first the second row, cross the third row, etc. So it's going to loop it along that sort of pattern. What I want to do is see how many different operations does it do. What's the time complexity of this? Now, there are different ways of counting operations, because there's lots of things that are happening in the code here. Let's make it simple. Let's just count arithmetic operations. Now, I know that there's more steps than that, which you can tell me in a second, but let's do arithmetic stuff. So, t equals 0 is not doing any arithmetic, really, so let's ignore that one. So, I equals 1, no arithmetic. Checking comparison, let's assume no arithmetic there. So, the first arithmetic line really is this one here. So how many different arithmetic operations are being performed in that line?
2.
2. So I'm doing an addition and a multiplication. There's 2 ops here. What about this one here?
1.
1. So in this loop, we're having 3 operations. For every time that loop happens, we're getting 3 operations happening. So therefore, for the whole inner loop here, so for this whole thing here, how many different operations are being performed? It would be 3 times the number of times it goes around the loop.
So it'd be 3n squared.
And so this inner loop here is just really going along one row. That's all it's doing. So it's just doing one row at a time for the moment. So it'd be 3 times by the n of that row. So it's 3 times n for the moment. Everyone okay with that? Then we've got another operation. So then we've got an I equals I plus 1.
So one operation.
So one more operation.
That happens n times.
And so that's that loop there. And that whole 3n plus 1, that's the thing happens. That happens another n times. So for every single row, we're going to do it. So we have to multiply all of that by n to give me my total number of operations all through brackets. And so the number of operations is 3n squared plus n. So that's the number of operations. And all we're doing is counting additions and multiplications. Now, in truth, checking the comparison is probably going to take maybe more. It would take just as much time as the other operations, but never mind that. It's got to count it somewhere or other. Why do I not have to worry about it? You can tell me in a second. But most of the time, you can care about the big O for that. So what is the big O for this algorithm?
N squared.
And so the fact that there's an n term in there, that doesn't grow nearly as much as n squared, so we just sort of drop it when we look at the big O. And again, the constant in front we can drop. So the big O for this is O(n) squared. So it's a quadratic function. And I could see it straight away, by the way. As soon as you're getting two nested loops, it's going to be big. It's going to be n squared, pretty much. N cubed. Now, even if I changed it so that j was less than or equal to I, which would be looping over a triangle rather than a square, if you did that sort of thing, it'd still have big O(n) squared. So two nested loops still end up being quadratic. That requires a little bit more effort to explain that. And I'm going to not explain it because that's one of the it gets alluded to in the assignment essentially. So the selection sort effectively does that sort of loop.
So basically, you would have been giving us an answer to the assignment.
Oh, not really.
Oh damn!
It's a bit more indirect than that.
Oh great, just what I needed.
I don't have to explain about some things. So you got a nested loop like that. A quadratic time is going to be pretty common. So I didn't count absolutely everything, as I said before. So I could have counted. If you want to look at how quickly it's going to take in real time, the comparisons will take some time, perhaps as much as the adding up, etc. But if you think about those, they would just add a constant for every bit of the loop. So although they change the number of breakings, they will not change the big O notation. So to get the sense of big O, you can be a bit sloppy if you're counting. If you actually want to know physically how long it's going to take, well, you have to be more precise. The problem with counting how long it's going to take in reality is that not all operations will take the same time. And certainly if you're using floating point. So if these are all integers, but if you start using floating point, the floating point operations take longer than everything else. And so counting operation at least is more appropriate if you've got lots of floating point. And I made the application simpler to avoid having to explain things, but that's more when you do that. So, why do we use big O notation? So it's good for comparing how things are going to go for large inputs.
Do we use big O because it's math?
No.
Damn.
It's about 100 years old. Yep.
Did the guy who figured it out, he was like, oh, and there he goes.
He had an epiphany. He was like, oh, damn.
And then when he found the other one, he was like, oh, that's why it's a little low.
Right, David.
Okay, so the idea came about 100 years ago. So predates computers.
During World War I, he was like,
no, before so maybe it's maybe 20 years before World War I. So maybe 130 years ago, that sort of time frame.
oh.
So you're looking at number theory. And they didn't use this notation. So that's what the concepts were developed for looking at the asymptotic growth. That's the fancy word for it. That we're doing here. And so Donald Knuth, or how you pronounce his name, I don't know, who's very good in data structures, was trying to look at how to compare different data structures in the 70s. and he was looking at how other people had done it in number theory, just related actually. And he goes, look, I like this way of describing some of it, so he just borrowed some notation directly. Others he disagreed with and changed it. So the notation we use today is very much from him. And so what I typeset this in is called a program called LaTeX, which he wrote with the original version of as well. So he was influential in lots of algorithms. So the algorithm that he liked to spend time on was how do you work out how to do page formatting? So when you work out when to break the page, which is an optimization problem. So you've got to go, I don't want to have too much, don't want to have a lot of white space at the bottom. So how do you where to choose where to have page breaks, etc. So that was what he did. So, but he also developed this big annotation, and so he was the one who chose the letters essentially, and he didn't pick them from thin air. He had to at least rely based on what other people had done before him, even though he twisted a bit what people had done. You know, he used a bit of license, but you can only go so far. But anyway, so it's really it's good for comparing stuff when you're looking at how things are going to go for large input. So it is a good simple comparison technique. By default, it really captures the worst case scenario because it's always really talking about the upper bound. So it's good for comparing worst cases. And like that last example showed, is even if you count things a little differently. So even if you don't care, look, some operations are quicker or slower than others, it ignores all that complexity at all. So it's just a nice, simple way of comparing stuff. So it's actually quite simple on how to compare stuff. So they're all good strengths for it, which is why it's commonly used. It has some bad things though. So if you've got a recursive algorithm, which I'll talk about more in a second.
The big oh no.
That for recursive algorithms, how recursive algorithms work is they start with a big set and they break it down into smaller ones as you're going along. And so how that algorithm actually runs in the small data sets actually does make a big difference in how it actually runs. And Big O really ignores that part. And so for comparing sorting algorithms, for example, so a lot of the more efficient sorting algorithms are recursive. And how they behave with the small stuff makes a difference in actually how it runs in real time. And so the sorting algorithm for Java, for example, and Python's pretty similar, is it starts with a efficient one for big stuff, which is some sort of merge sort. And so how merge sorts, it just breaks it down into lots of groups. And as it gets to a smaller block, it doesn't go, oh, I'm just going to stop doing merge sort anymore, I'll just do a selection sort. So it changes the algorithm as it gets smaller, because as it gets really small, so change it. So I think it's called a Tim sort. If you want to look it up, you're going to prove me wrong. What you shouldn't do. Which is the version of it. Now, so there is a combination. I may have got the bottom one incorrect, but that's the sort of idea, because Big O only really looks at the large case, and where in a real implementation you have to have a balance there. Other times is Big O really is measuring the worst case scenario. So there's some algorithms that would run better than what the Big O would suggest. And the best example of this is called the quick sort algorithm. So the quick sort, worst case is Big O of n squared. And so so quick sort basically partitions data into two groups and then puts all the small ones below the partition, all the big ones above the partition. If in a bad situation, you might just pick the partition wrong every single time, and you get the whole code blows out. It doesn't happen very often. So although that is the worst case, on average, quicksort is n log n. And because quicksort has lots of other tricks to it, it actually works quicker than some of the other algorithms, even though the Big O would suggest otherwise. So Big O is not the whole story. So often how they report quicksort to show that it is good after all is they report the average cost rather than the worst case. They look at how the average grows rather than just the worst case grows. That's the way of overcoming that. And other cases for Big O is sometimes when you're, say, adding elements to an array, most time when you're adding something to the end of an array, it happens in constant time. Occasionally though, you hit the end of the array and you have to allocate more memory, so increase the capacity, copy all the elements in the current array over to the new one. That takes a bit more time. So most of the time, operations will be constant time. Occasionally, you get one that's linear. And so you need to, and so big O, what I consider worst case, where in the grand scheme of things, just looking at the average would be much more sensible in certain circumstances. Now, realising it works quickly most of the time and occasionally has a big lag is important to understand. And sometimes when you don't want any lags at all, you wouldn't do that implementation. So you've got to work out if that matches your real-time performance needs or not. So sometimes you want to have consistent performance. Like if you're designing a phone app, for example, if the program appears to be hanging just because it's had a big array for a moment, your user might just give up on it. So you need to be mindful of where you try to compare it for. And so the last thing is when you are comparing two similar algorithms, if the big O might be the same, but how they might be different is the constant multiple in front of it, which you can't see for big O, it gets hidden. Right? And understanding that is a good way of trying to appreciate which algorithm is actually better. So there's some things. So how we have a break, 5 minutes, then we'll start talking briefly about recursion for a while. Talk about is Towers of Hanoi briefly, but the bigger purpose I'm looking at is the idea of recursion, which is a computer science idea, and the idea of recurrence relationships, which matches well with recursion, but it uses them more general as well. So I was using Towers of Hanoi just as an example, just to introduce those concepts, essentially. So Towers of Hanoi, which most people sound like familiar with,
It can't be all at once.
is you've got 3 different sticks, a source, a spare, and a target sort of thing. And you've got, basically the idea is you have to move 1 ring at a time. So I'll flatten it down. So I've got 1, 2, 3, 4, I've got 4 rings here. I'd like to move these 4 rings from my source peg to my target peg, and I can use the spare one, I'll have to use it. The requirements are, when you're moving the rings, you always have to have the biggest disc on the bottom. So you can't have, so in this particular case, the first step would be to move this small one over to the spare peg. This next one here is a bigger disc, you can't move it on top of that small one. So you really are forced to move it over to here, for example. So what I want to do is I want to work out a few things. One, I want to make a strategy for solving it always. I want to code up the algorithm for solving it. And then the other thing is, once I've coded that algorithm I would like to work out what the big O for that algorithm is. So how many steps are required to actually solve it, the different number of disks you have. Those are the 2 things I'm going to do. So let's talk about big picture of what we're trying to do. If I want to move those 4 disks from the peg on the left to the peg on the right, pretty much I really have to move that big disk at some point in time. So let's just focus on the big disk. So what arrangement do I have to do before I can move the big disk?
You got to get all 3 other disks off the top of it?
Yep, and where do I have to put them?
On 1 peg.
Yeah, I have to put them all on the peg. So these 3 here, I'm going to have to move all of these onto one of the pegs. Which one do I have to move it onto?
Spare.
The spare one. So I have to move all those 3 onto the spare peg. That's the first thing I have to do. That's the big picture of the algorithm. I'll worry about later how I'm going to do that. I'll worry about that later, but just do the big picture for the moment. That's step 1, really, or lots of steps. The next thing I want to do is I have to move that big disk. So I move this big disk over onto my last peg. That was step 2. That really is one single step. And the last thing in terms of big picture of what I'm trying to do is now I've got my pile, I just put it back on top. So I put that pile back on top. So there are 3 stages to solving it. not 3 steps, 3 stages to solve it. That's the big picture of what we're trying to do. So how about I try coding it up? Since coding looks pretty boring to type up, I'm just going to show it to you. But that's just the basic idea. So my algorithms is just pseudocode. Towers of Hanoi, I'm trying to move n disks from a certain peg to another peg, and I've got another one as spare. You can cut it more efficiently than this, but that's the basic idea. So most of the time I want to use that 3-step process. That is, I'm going to move the top, if I had 4 disks, I'm going to move the top 3 from my first peg onto the spare, using the 2 peg as the spare instead. That's the first thing I want to do. That was stage 1, moving the whole tower across. Then I'm going to move my big one on the bottom, and then lastly I'm going to move that tower back onto the big disk again. So those 3 lines, 1, 2, 3, are those 3 stages I just talked about. So as you can see, what I've done here is that in order to write down the solution for it, I'm actually referring back to the algorithm for itself. So when it refers back to itself, or a function calls itself, it's called a recursive function. Have you guys seen that in any of your programming subjects?
Yep.
Okay, yeah. And so you can always program without recursive if you wanted to. You can always get rid of it. But it's often much easier to understand the code when you do it, etc. So it's a good technique. When you do the recursion, you need to have a way of it stop calling itself. Otherwise, you'll get an infinite loop effectively in the system, and you only get, you get a stack pointer, how many functions it is, goes off the end or something like that. That's what normally happens in practice. So you need to have a way of stopping the recursion. So in this case here, I would like to stop having that 3-step process. Well, the stop case is when it gets simpler. So the simpler case is when I actually have nothing on top anymore. So I only got to the 1 big disk to move, and I don't have 3 steps anymore, I only just got 1. And so I need to have a separate case. That's what the top line here is, when it just goes down to something simpler. So if I only got 1 big disk, I just have to move that disk, and that's all I have to do. So that's a recursive function that calls itself. So if I had Towers of Hanoi calling it with 3 here, it would run it the same function with a value of 2 here, which would then call it with these with 1, etc. So it actually calls it many times. And so what I want to do is, now I've got a recursive function, I'd like to work out how many times this would run. So in this case, number of moves. How many times does it call the function move disk, essentially, to run this? So for that end, let's just define a few things. So let AN be the number of move disks per pile of size n. What's A1? So how many move disks are required to move a pile of size 1? 1. So that's just basically moving the disk from where you need it to be, from where you want it to be, where it is to where you want it to be. That's an easy one. Other times is to lose this algorithm. So look at my code. So the number of times this whole function would use move disk would be A to the n. That's what the definition is. So if you look in it, if n's not 1, it'll give any else clause. So it'll be in this else clause here. So the else clause would be, it'll first run Towers of Hanoi with n minus 1. So the number of moved disks would be how many of the moved disks that would produce. Which would be, well, A to the n minus 1. So however many times you would call it for n minus 1, that's what it would be. I don't know what it is yet, but since it refers back to itself, that's what the case is. So that line, this line here, would call the move disk function A to the n minus 1 times. I'm yet to work out what it is, but that's what it's going to be in general. How many times does this next line call move disk? So this line here, how many times does that call move disk? What's one? You can see it. I can see it right there. It's just there's only one of them. So there's a +1. What is next line in the else clause? How many times does that call the move disk function? Well, n minus 1, that's right. So that's basically so that's what all I've done is just translated that function into number of steps to take. So the A1 equals 1 really is the first line, is the if clause, and the other one comes from the else clause. That's all I'm accounting for. So now let's simplify it down a bit. So if I simplify this expression, I get a to the n is equal to 2a to the n minus 1 plus 1, and a1 equals 1. So the number of steps, number of move disks required for this function is given by that set of equations. So this is called a recurrence relation. I'm not spelling properly. So recurrence relation or recurrence relationship, either or. So I would like to work out, the equation's useful and you can do stuff with it. I actually would like to solve it. So let's just have a thoughts how to do that. So the two things I'm looking at here is one is recursion. They're an algorithm or a function which calls back itself, just refers to itself. And the other one is a recurrence relation, which is an equation which is for a number sequence which refers to itself. So related ideas. And so a number of ways of trying to count the time complexity for a recursive algorithm commonly is using recurrent relationships, which is that's the main, that's where we're coming from it. It's useful for other things too, as I mentioned later. Okay, so that's what we're trying to solve. Let's work out a few things. Just see if the pattern. Let's work what A2 is. We can work out other values just by subbing into the equation merely. So subbing into the equation, I just replace that equation, instead of being n, I just replace all the n's by 2s essentially. So I get 2 times by A, what? What's 2 minus 1? 1. Plus 1. So all I've done is in this top equation, I just replace n by 2. What's A1? 1. So that's going to be 2 times by 1 plus 1 equals 3. So what that says, if you've got 3 pegs and you've got 2 disks on them, it requires 3 moves to move it across. And the 3 moves are move the little disk to the middle, big one over, move the little one back on. That's the 3 moves. So that's what it's trying to say. How many moves are required if you've got 3 disks? Would it be 2 times by A, and I'm really just subbing this equation again. So it's A to the n minus 1. N minus 1 in this case would be 2 plus 1. So it'd be 2 times by 3 plus 1, which is equal to 7. So it requires 7 moves to move the 3 disks over. And you can do bigger ones, right? So you could just plug a few numbers, keep going, and you can work out what A to the 4 is. So A to the 4, which Jake was saying before, is 15. And A to the 5 is 31, and it keeps going. And 63 is the next one, that's right. So what's the pattern? You might notice it.
Should we do the n minus 1?
Okay, so...
Thanks, Trevor.
It's all good.
So, looking at the pattern, we can see that ADN, or we guess really, ADN is 2 to the power of n minus 1. That actually matches all the numbers we can think of, And we can prove it by actually plugging that number into those two equations to see it works. That's how you can actually prove it. That's one way of doing it. Now, so if you've got a nice pattern, you can do that. But what I want to do is look at different ways of trying to generate that by itself. So what this is called the recurrence relation, and it's an equation. What I really want to do normally is I like to solve it. That is, I like to find an is equal to some function of n directly. I don't want it to refer to itself, I just want to know what the answer is. So what I've done here, more through guessing than anything else ultimately, or by looking at the pattern and using the pattern to infer it, I've worked out what the answer is, but I have solved it. So that's the sort of thing I want to do ultimately. And I want to develop some techniques to do that as well. And so I'll look at two main techniques for solving these things: the characteristic equation method, which I'm sure you'll like the best, and the generating function method, which you probably won't like, but it is much more generalisable, so it works in many more circumstances, which is why I want to mention it. In your assessment, this includes the exam and your assignment 4, you can choose which one you'll do. So I'll leave the choice to you. I will mention both too. Okay. Recursive algorithms, they're algorithms or functions which call themselves back. Examples we've seen in this subject, apart from ones you've already done, would be graph traversals, so doing an in-order or a post-order or pre-order traversals would all be done by recursive functions. So you go, I want to do the left. So in-order would be left, parent, right. So when you do the left, you call in the whole function again. So it's really just a conversion. Adding something to a binary search tree is again would be done by a recursive function. What recursive things have you done in other subjects? You mentioned you've done them. Can you remember what they were? That's a harder question.
Recursive sort algorithms, what I did a while ago.
Okay.
That's it. Not really in class.
Okay, so lots of the sort algorithms, lots of the high level, the better sort algorithms that tend to be recursive. Yep, sorry. So in general, I want to better consider recurrence relationships. So recurrence relationships really are looking at a sequence of numbers that you index by an integer. Sometimes you want to start them at 0, sometimes you start them at 1. Doesn't make much difference really. So I've got a bunch of numbers, so A0, A1, A2, so just a bunch of numbers. And they're indexed by the countable numbers. So a recurrence relationship is an equation which defines A to the n in terms of other numbers in the sequence. So A to the n is equal to some function, say n to the n minus 1, and maybe n to the n minus 2, etc. That's the rough idea. I'll define it more formally in tomorrow's lecture. So that's the idea of a recurrence relationship. And most of the time, you have the equation, like you can see here. You also tend to have what's called an initial condition, i.e. the starting point of the sequence. You know what the bottom of A of the sequence is. So in this case, we know that A1 equals 1 was the start of the sequence. So you start, and then some pattern to work out all the other values are from that. And our goal is to learn how to solve these things in certain cases. So before we do that, let's look at some examples to muck around with it. What's one more thing I was going to say with it? So just some examples of recurrent relations or relationships. They're useful in terms of working out time complexity for algorithms. I guess that's what we have in our mind, like the towers of Hanoi example. But you can do another thing, like counting. So if W is the number of ways to order n things, you can get a recurrence relationship for that. So you have an initial condition, so the number of ways of ordering nothing, well, there's triply one way of ordering nothing, it's there already.
Is there though? You just order nothing.
Hello waiter, I would like nothing.
So it's almost definition perhaps than anything else. So if you don't like that, you can just say the number of ways of sorting one thing is equal to, what's W1 equal to then?
Yes, one.
Right, okay, maybe we can start there if you don't like the other way. Then the number of ways of sorting n things is firstly you pick one element to be the beginning. There's n choices for that. And then you sort the other n minus things out. And so the number of ways of sorting n things is equal to n times by the number of ways of sorting n minus 1. So what I've done here is set up a recurrence relation to define counting n things. And you can do it for lots of counting. So what's the solution for that? What's the direct formula for Wn? That's the equation. You have to solve it. So Wn would be equal to something just ends only. How many ways are there of ordering n things? N factorial, that's right. Which is a revision for what we did a month ago now, probably.
So basically 10 years ago. Like,
well, it might feel like 10 years. It wasn't 10 years ago, but it might feel that way. So you can use recurrence relations for lots of things. So as I said, counting. You can do it for population growth. Fibonacci series, as the F stands for. An example where the original example of Fibonacci series was Fn is the number of pairs of rabbits that are alive in a given month. And you want to see how they grow. So rabbits
very fast.
breed, and so they will increase from each month.
Exponentially.
Yes. So there's lots of applications, and so although we think of it in terms of computers initially, they are useful in many circumstances. And so some of the applications that you consider in your assessment items will look at some of these other ones. So it's all just about computer code. So let's look at some special cases. We'll solve these, and that will probably be a time for the day. And then once I've got some special cases, then I want to look at what's the general technique of solving these sorts of things. Well, we're going to feel for it for a moment. Let's do the first one. So this is B's. To get the idea of the pattern, let's just muck around or just plug a few numbers in and see if we can guess the pattern. So first one, B1 is 2. What's B2? Well, the equation basically adds 6 to the previous number. So be 2 plus 6, or 8. B3 would be
14.
So you add another 6. So 2 plus 6 plus 6, which is 14. B4 would be 20. Etc. Now, what am I writing that funny way? Because I'm trying to see the pattern for it. Now, you might be able to see it from the 2, 8, 14, 20. You might see it from that too, of course. So, what's the general pattern? What do you reckon B, the n, is going to be equal to? You're trying to describe
2 plus...
It's going to be 2 plus something, yep.
6 times n minus 1.
Yep. So if you look at it, the number of 6s we have is increasing by 1 every time. So when we had 4, we had 3 6s. When we had 3, we had 2 6s. So the number of 6s we have is 1 less than the n we have at the bottom. So the general pattern is 2 plus 6 times n minus 1. So, what do we notice about something? Let's take the difference. Let's do the difference between these numbers. What's the difference between 8 and 2?
6.
6. 14 minus 8?
6.
20 minus 14? 6. So, for this is an example where the difference between all the numbers and the terms is the same. So, everyone know what this sort of sequence is called?
It's a
Yep, that's right.
arithmetic series.
We don't use the sequence, we're not adding them up. So it's called an arithmetic progression or arithmetic sequence. Arithmetic's the key word, which you got right.
Yeah.
Well done. So anyone else remember arithmetic sequences?
1, 2,
Some
3, 4.
duple nods. So some recurrence relationships are arithmetic, so they're just growing at constant difference every single time. And number 2 here really is that. That's an arithmetic progression in just one.
I don't need any more than that. I'm already wrecked as it is.
So that's an example of arithmetic progression is 1 and 2 are both arithmetic progressions, and you can see that this one here is just the general case of the first one. So it's replacing 2 and 6 by just general letters instead. And so c to the n would be the first term plus n minus 1 of the d is the solution for it, in very much the same way we did there. We won't actually deal with method that much in this subject. The one we deal with more are the next two. The third one. This one, D1 is 2. D2 is, so what happens in this case, instead of adding 6, you multiply by 6. So it's going to be 2 times by 6, which is 12. D3 would be 2 times 6 times 6, which is 72. And D4 would be 2 times by 6 times by 6 times by 6. So there's 3 of them running the room here. So what was that? 4, 32. And it keeps going up. What's the general pattern? What's the formula for D to the N? And again, it's easier to see the pattern maybe from these numbers at the top. So they all have 2's in them.
2 times 6 to the power of n minus 1.
Yeah. So there's always 6 to some power, and there's 1 less 6 than there is the n. So it's going to be 6 to the n minus 1. And for 4, it's the same sort of thing. Instead of 2, you've got A. Instead of 6, you've got R. So the solution is the same sort of thing. It's going to be A to the R to the power of n minus 1. Or more generally, perhaps, it's going to be something or other times by R to the n. I guess more really broadly speaking. What a roll of that, I'll explain in a second. So, in terms of these two here, if you do the ratio of these numbers, so what's 12 divided by 2?
6.
72 divided by 12?
6.
And 432 divided by 72 is also 6. That might be hard to see. So these have a constant ratio. So these are called geometric progressions or geometric sequences. We will deal with, that's what we tend to deal with. So geometric sequences have the solution of a constant times by a number to the power of n. That's the general sort of